Uh, Welcome everyone. Today we are very happy to have Yizhi You from Northeastern to be our keynote speaker. And she will tell us about her recent work on quantum circuit and state preparation. So let's welcome the speaker. Go ahead.
Thank you. Thanks, Rochen, for the introductions, and thank Rochen and Ruben for the invitation. And today we'll talk about the state preparation via quantum circuit from a space-time duality picture. So before I proceed, let me introduce and acknowledge my collaborator who bring about such kind of quantum circuit issue. This work was in collaboration with Sarang from Yizhi You department at Princeton, and also Peter Lu, who was previously in Perimeter Institute and now in U Maryland. So nowadays, the quantum state preparation becomes a very popular topic. And how do we prepare many wave functions that have long-range entanglement and long-range correlation have been a central goal, because these type of wave functions turn out to be a very useful resource for doing something like measurement-based quantum computing or other quantum information processing tasks. And in the past few years, a lot of proposals, including some people here, have been bring about on how to prepare long-range entangled many wave functions in a scalable and programmable quantum simulators. And today, we will only mention two types of proposal. One was known as the sequential circuit, which is a linear depth unitary circuit, which was pretty well known in the quantum information communities. And recently, some people like Xie Chen and Mike Hermley bring about this issue to the condensed matter community because it had a lot of intriguing interplay with the non-invertible symmetries. And the other is known as the measurement feedback circuit, which was proposed by Ruben Verreisen a few years ago. And there was a similar proposal from the Perimeter group by Peter Lu, which is a shallow and non-unitary circuit where they use measurement as a shortcut. So let me just have a brief introduction of what is quantum circuit. In quantum mechanics, we know that two types of wave functions that live in the same Hilbert space can always be connected by a unitary operators. And such kind of unitary operators could be viewed as a unitary time evolution of a Hamiltonian. And if I discretize the time into different segments, in each segment, the unitary time evolution is more like a bunch of unitary gate that act on the initial state. And if we repeat these patterns and apply the unitary gate from time to time, finally, we form a unitary circuit that transforms, say, an entangled tensor product state to some highly entangled wave functions. And for a unitary circuit, there is an important and well-known theorem as the Lieb-Robinson bound, which tells you that if my circuit only involves a bunch of unitary, local unitary gate in each step, and after finite time evolution, if I begin with an unentangled state, after finite time evolutions, the entanglement can only appear within these light cones. So if I pick up two qubits within these light cones, I expect them to have some mutual informations, but no long-range mutual information can appear outside of the Lieb-Robinson cone. And because of that, if I want to generate a long-range correlated state in the thermodynamic limit, probably I would usually linear depth circuit. And there are different type of linear depth circuit. The one specific type of linear depth circuit I will introduce today is the sequential circuit. The logic is pretty simple. So for the sequential circuit, in each steps, I only entangled two local degree of freedom. Say in the first step, I entangled the first and second qubit, and then entangled second and third qubit, and repeat these patterns. So this is a linear depth circuit which can generate long-range correlation and long-range entangled wave functions. But because I only have finite number of gates involved in each steps, such kind of sequential circuit would always generate a wave function that preserves the area law entanglement. For example, if I begin with a spin polarized plus state and apply the X and ZZ gate repeatedly in such kind of sequential depths, the first step, I'm indeed doing some control gate, which force the first and second bit to be aligned to each other in SZ directions, and hence entangled first and second. And if I repeat this process, generate correlation between different qubits sequentially and eventually end up with a GHZ state. So the sequential circuit requires n number of steps, which scales with the system size. And for sometimes people were wondering, is there a way for us to escape from such kind of linear depth circuit, but still end up with the same type of long-range entangled wave function, like a GHZ type of cat state? And one of the shortcuts for that is if we get rid of unitary and think about non-unitary gate. Non-unitary gate is actually a pretty common thing in STATMAC. Like if I think about thermodynamics, the thermal partition function is something like a non-unitary operators. And if I go to zero temperature, this is indeed a projection operators which can project the ground state into some highly entangled wave functions. So this was the original proposal by Ruben Vereson and also Nat a few years ago. And for the measurement feedback circuit, we first begin with some type of entangled qubits. And we only apply a shallow unitary. So in his original protocol, we only apply CZ gate on every two adjacent qubits. And after two steps, this is actually one step because all of the CZ gate do commute each other. We just get a locally entangled wave function, which can be written as the ground state of a 1D stabilizer code. And this is a locally entangled wave function. It doesn't have any long-range mutual information, but it has some type of hidden order or conditional mutual information. If I decompose the system qubits on the chain into even versus odd lattice and denote them as the red and blue color, it has a actually decorated domain wall picture. For every two adjacent even side, which are the blue dot, depending on whether they are antiparallel to each other, then the red qubits that sit in between them are in the minus X state. And suppose they turn out to be parallel to each other, then it is decorated with a plus state. So this wave function doesn't have long-range entanglement, but there's still some type of conditional mutual information in between them. And the next step is I have to do something non-unitary. Can do a measurement on all of the qubits that live on the odd sublattice. So I just measure all of the red bit in the SX spaces. And after each round of measurement, I get a random result. Say this is my final random result. Once the patterns, whether in the plus or minus X state, are already pinned, then these spin patterns, whether they are parallel or anti-parallel to each other, would be pinned as well. And hence, post-measurement, what I get is I actually get some type of GHZ cat state, which is a superposition of some type of domain wall patterns, depending on whether I put a plus, whether my measurement result is plus or minus here, together with the time reversal partner. So in this process, the measurement, which is more like with post-selection, which is more like a projection operator, plays a role as a shortcut, which eventually engendered a long-range entangled state.
Sorry, but if I include the measuring device, isn't it still a unitary?
Mm-hmm. Once you make a measurement first, like make a measurement and get a post-selections, this process itself is non-unitary. Like if I measure this and get plus this.
But if I included the coupling to the measuring device, would it really be different than the previous just applying sequential unitaries? If I include the coupling to the measuring apparatus?
Well, what is including?
So you have some measurement, right? So measurement means you entangle your system with a measuring device. That's what measurement is. Right?
Yes, and I have to read the result rather than just entangle them. If you just entangle them without knowing the result, like where does the device, or usually sometimes we call it environment, is doing, this is more like a quantum channel which engender it into a mixed state.
Maybe one general comment on Clay's question is, if you try to interpret from the total unitary point of view, the measurement is actually doing a non-local operation because it's gathering all the information into one place, like your brain. And that would actually be like a non-local circuit. So now the locality is only in
This is how you're going to break the bound.
Yeah.
Nice. Thank you. Yeah.
Okay, and what I want to talk about is want to ask a simple question. Is there any general relation between a sequential circuit, which is a linear depth unitary operator, versus a measurement feedback circuit, which is a shallow non-unitary gate? And is there an inverse relation between them? And today I will just answer the simple questions and demonstrating that these two types of protocols are actually related in terms of the space-time duality picture. So when we talk about space-time duality or something like a Lorentz rotation, usually think about we have a QFT and exchange the position of time and x direction. Let's look at what happens if we have a space-time duality of a unitary gate. So suppose I'm thinking about a two-body unitary where I have two input bits labeled as I1 and 2, and after a unitary operators, they are somewhat entangled, disentangled, and get two output state that are labeled as O. And this is the x direction where we have two qubits, and this is the time direction. Now I just exchange the space-time. So x2 that is my new time direction, and this is my new spatial direction, and this is my new time directions. And then the input state are the two qubits that live on the left, and output state are the two qubits that live on the right. And such kind of operators, if I do a space-time rotation of a unitary two-body gate, the dual gate would usually, in general, be a non-unitary gate. For example, the simplest unitary gate we can think about is identical operators, where the first bit does not change after time evolution, and I just denote it as a straight line connecting the bit from different times, and same for the second bit. If I make a space-time rotation, these are the input and these are the output state. And for the previous time direction, a line I plot here actually indicates that the first bit at time t equals 0 and t equals 1 are identical. And if I do a space-time rotation, this actually means that the first bit and the second bit that are spatially separate along x direction are identical. And this can be treated as a symmetric EPR pairs. So an identity operators under space-time rotation becomes a projection operator that project two qubits into a symmetric EPR pairs. And of course, there are certain type of gates that are dual unitary. The simplest thing you can think about is a swap gate, which exchange the first and the second bit. And if you do a rotations, it's still the swap gate. Okay, and after realizing that the space-time rotation of a unitary operator in general becomes a non-unitary operator, then let me revisit the sequential circuit. This is a unitary operators that is highly non-local and scale with the system size. And for measurement feedback circuit, what we are dealing with is a finite depth, and sometimes quantum information people call it shallow non-unitary gate. One is unitary, one is non-unitary. One has a linear depth and the other has only finite depth. And the question is, can we just do a bare space-time rotation and see whether a linear depth unitary circuit as a sequential circuit can become such kind of finite depth non-unitary? So the thing I will do is pretty simple, just to exchange the space-time. And before I proceed, let me clarify my notation here. So for the standard sequential circuit, they usually have such type of break patterns. The first step, I entangle the first and second, and in the nth step, I entangle the nth qubit with the n plus 1 qubit. And in my notation throughout the talk, I would always add or incorporate a swap gate with the unitary operator in each step. It doesn't change anything. It doesn't change the sequential nature and still produce an area law entangled state. And the only reason I include a swap gate is graphically, such kind of sequential circuit can be represented in this way, where in the first step, I entangle the first and second qubit. The second step, I entangle the first and third. And finally, I entangle the first and nth qubit. So this is another way for me to represent sequential circuit by incorporating everything with a swap gate. And the only reason I adopt this notation is after space-time rotation, it will be easier to see.
So I guess if you have trapped ions or something with all-to-all connectivity, this would work. But if you have only local gates, then you would have to decompose the long swaps into bunch of 2-qubit swaps, which would
Correct.
Right?
Correct. So in reality, such type of gate where you just have to entangle the first bit with the final bit, it's pretty hard. But graphically, these two are the same. This is equivalent as in each step, I just absorb or incorporate a swap gate into the two-body unitary. And these two are the same up to some global shift, because a bunch of swap gate it's more like a global translation of one lattice unit cell. So the final state is not that qualitatively different. Okay, and in this notation, let's revisit what does the sequential circuit look like if I want a GHZ state. So suppose I begin everything that is polarized in the X direction. The sequential gate in each step entangle the first and the nth bit. And for 1D, it's a two-body gate. And the structure is, this is more like a control gate, where the first bit is always a control gate. It doesn't change under such kind of unitary if I write everything in SZ basis, but because I have a swap gate, it just changes location to the diagonal direction. And the second bit, which comes from the nth bit, is more like a target bit. Depending on the position, depending on the orientation of the first bit, whether it is in the plus Z or minus Z direction, I implement SY rotation with pi over 2 or minus pi over 2 to make them align to each other in the SZ direction. And if I apply such kind of sequential gate, what I'm doing is I always treat the first bit as a control bit and the nth bit as a target bit, which I try to make them align with the first bit in the SZ direction. And eventually I get a symmetric GHZ state. Okay, now let's just do the simple thing. We do a space-time rotation. Previously, my notation of sequential circuit, this is X direction and this is the T direction. And now I just want to swap X and T by either rotate your net and look in this direction or just rotate my figure in this way. And in the new notation, this is the T bar direction, which came from the previous X direction. And this X bar direction came from the previous T direction. And this is my new time direction. This is my new X direction. Along the X direction, I have a bunch of qubits. And at T equals 0, these qubits, let me label them with bright green colors, are a bunch of bits which are prepared in terms of EPR pairs. And these type of qubits actually all correspond to the first qubits along the sequential circuit between two time intervals. And previously, before and after apply the first and second sequential gate, I have a bit which does not change over time. So it's just the identity time evolution. This time segment and next time segment, they turn out to be the same. And if I rotate them in X direction, that becomes this and this qubit, which are spatially separate along the X-axis. And in time direction, they are the same, just encounter with a unitary time evolution. In the spatial direction, that corresponds to the fact that these two turn out to be a symmetric EPR pair. They're entangled and turn out to be the same, that the left spin and the right spins.
What do you mean it turns out to be? How do you derive that? I don't understand what this map is that you're using.
So this is the time directions, like I have input and output.
Yeah.
And if I do it,
So in this tensor fracture on the left, you just have a bunch of ups or whatever. And why does that correspond to starting with the initial state that's a sum of ups?
it's not a sum of ups. So for every two dot.
But why a sum at all? What how did you get from a factor in a tensor product to a particular state?
So the factor of tensor product, do you refer to this one or this one?
The one on the left. The green dots on the left, they're just there's some tensor factor in a tensor product Hilbert space. And they're the control gates. And then how do you get to a particular state in the right?
So this is the time evolution of the
Yeah.
first bit between two intervals that I don't do anything.
Yes.
So at T equals 0, I'm at I state, and T equals 1, I'm at I state,
Mhm.
and sum over all possible I because I have all possible input and get output. And here I'm 2-bit that are separate along the X directions. And if this is I, this is also I, and it's a sum of I. And
Why is it a sum?
Because
the left hand side, the information associated to the green dots on the left and the right seems completely different. On the right, the information is a state at a fixed time in this tensor product Hilbert space. And in the left, it's just some factor in this tensor product Hilbert space. What is the relation between them?
The left is a time evolution operator.
yes, so it's an identity operator. So between this and this is connected by identity operator. And identity operator, my input cat and output bra have once you choose basis, you have to take out all of the bases and then get an identity operator.
I wonder if it can be helpful to go back. Yeah, a few slides ago, you had the helpful picture of the identity and the Bell state projector. That's kind of the submodule, right? Of what you're using.
Yes, identity operator just becomes symmetric EPR pair. And when I have identity operator is write it in the operator sense. This is I choose whatever basis, sum over I. And once I do that space-time rotation, this is more like the Choline isomorphism, where this, if you convert it to the Brown, where this is at I site, this is at I plus 1 site. This is a symmetric EPR. So my input state becomes a bunch of symmetric EPR pairs. And these symmetric EPR pairs came from the fact that in the sequential circuit, between 2 time intervals, I'm just doing identity time evolution. And this is the time direction. So I have this input state and I add a Q operators, which is a 2-body operator, which that doesn't need to be unitary, and finally get these output state. So if I label them in terms of the red dot, in the dual circuit, the output state are labeled as red dot, and I still denote them as a hollow one and the solid one, which live on something like an even and odd sublattice. And in the original language, all of the solid ones, the odd ones, correspond to my input state of the sequential circuit that is usually fixed to be some type of tensor product state. And these hollow ones are actually the output state of the sequential circuit. And this Q, depending on the specific form of the U, it can be a unitary or non-unitary operators. So in this process, what I'm doing is for the original sequential circuit, apart from the first qubit, I have a bunch of input and output state. And in the dual circuit, all of them become output state. They just live on the even and odd lattice. And the time evolution of the first bit between 2 sequential intervals now becomes my input state. This is more like an EPR state as an input state. So if I graphically represent this dual unitary gate in a more compact form, initially, I first prepare a bunch of EPR pairs, and then I apply these Q unitary gate. Initial EPR pairs are entangled between even and odd side, and this Q gate only appears between every odd and even side. So these Q gate, no matter whether they're unitary or not, at least they don't overlap, and this can be implemented by one step. And after that, my odd side are actually the input state of the sequential circuit, and the hollow side, the hollow red dot, or the even sublattice are actually the output state of my sequential circuit. And in particular, if I'm considering a special type of unitary, which is a control gate, together combined with a swap gate, under space-time rotation, the Q gate is always unitary and usually look identical to itself up to some Hermitian conjugate. So the Q gate, at least if your original unitary gate is some type of control gate together with a swap gate, the dual is always a unitary. So the protocol is something like I begin with a bunch of EPR pair, which can be prepared by one depth. And then I apply a Q gate, which is a dual unitary gate. And after that, what I will do is I will do projective measurement. Later, I will talk about whether we can do it from measurement and feedback to project all of the solid dot, which live on one of the sublattice, to the plus state. This process is to match my input state, because for my sequential circuit, these solid red dot are my input state, and they are pinned to be a plus state. This is my fixed input state. And once I project these bits into the plus state, the posted projected wave functions for the qubits live on the other sublattice exactly match the output state of the sequential circuit.
But if the main goal is to rewrite the sequential circuit as this kind of constant depth non-unitary guy, I'm just trying to, like, if one hadn't used this duality transform, and I'd just written the sequential unitary as like a MPO, do you know what I mean by MPO?
Yes.
Like, wouldn't that be a more direct way of getting kind of bell pairs and gates?
Yes, actually, later I will talk about whether the measurement feedback circuit can go back to sequential circuit. This is the picture. And it's something like, this is more like a MPS. It's a MPS that can be prepared by a unitary gate. And once you connect them in time and in measurement protocol, this is project every 2 qubit into the EPR pair. Yeah, this is the later part. So if I do a space-time rotations of the sequential circuit, what I get is I first get a bunch of EPR pair which can be prepared by 1 depth of unitary, and then apply another layer. This eventually end up with a shallow unitary. And then I do measurement on all of the even qubits, which I want to match them to the input state of the sequential circuit. After this step, then the output state or the post-measurement state are exactly the same as the output state of the sequential circuit. So in this protocol, the dual circuit is actually a shallow non-unitary circuit. It can be composed into 2 steps. The first step is I just apply a shallow unitary to let them locally entangled, end up with a short-range entangled state. And then to match the input state, I have to project one of the qubits live on the odd sublattice into a specific pattern, say project all of them to the plus state. And the outstanding question is, before I do the projection, what does the shallow unitary does, and what type of short-range entangled state does it bring about? And the second is, when I say I want to project them to the plus state, it's pretty hard to implement in real labs, because if I want all of the outcome to be plus, I probably have to do some type of post-selections. And the question is, can I always overcome such kind of close selections by some type of measurement feedback protocol?
So interject. So you're saying Q is unitary? Is that the state?
Q is not unitary, but if my original sequential unitary gate is a control gate, and then I always add a swap gate, then it is always unitary, because if I write them explicitly, the former control gate doesn't change, but change here, then they look identical to each other actually.
Thank you.
But only for this. And the control gate is fairly enough to generate a lot of state, especially for some type of stabilizer code or CASS code. The way we generate them is we figure out the right control gate that satisfies the local constraint. So the question I want to answer is, what does the shallow unitary does? So of course, if you know the explicit form of U, then you can always do the space-time rotation and write down Q and look at it and figure out what is the output state. However, for the sequential circuit that generate a GHZ state or other type of long-range entangled state that turn out to be some symmetry breaking GHZ state or topological order state, the sequential circuit actually implement a role as the primary linear duality. So for the sequential circuit, in terms of operators, the sequential circuit that generate a GHZ state, it implement a primary linear duality such that before I implement the gate, if I have an X operators, after such type of primary linear duality, they become the ZZ operators. And in my dual gate, both the input bit and output bit turn out to be my output bit, but they just live on different even and odd sublattice. So the sequential circuit that implement a primary linear duality and change X to ZZ.
Oh, sorry, that one
X to ZZ in the dual gate actually tells you that ZXZ stabilizer on these clusters have to be 1.
Sorry, just a question there. So mustn't the second Z must be on the same pin gate, right? Otherwise they're causally disconnected. Or am I misunderstanding? Is it not a single X pushing through to 2 Z's on the opposite side of that pink U?
Which part are you referring?
Just the red, red X pushing through. I would expect it ZZ on a single gate. Otherwise, how
yes,
can
for the original sequential circuit, yes. But if I incorporate a swap gate throughout this process, I'm actually doing a global shift. So doing a unit lattice cell translation. That is why I have this output. If you do the usual sequential circuit that entangle the n plus 1, then it should be Z and the Z in front of that. This is something like I use my convention. And likewise, the sequential circuit that implement primary linear duality always change ZZ operator to the X operators before and after that. And in my dual circuit, both the input qubits, which live here, and output qubits live here, are all output qubits. They just live on even and odd sublattice. So ZZ operators becomes X operator, which is nothing but a Kramer-Wanier duality, becomes a constraint that ZXZ on the other type of stabilizer must be unit. And hence that actually tells you that the final state, short range entangled state you have is just the Brown state of the ZXZ stabilizers. And hence, after I apply such kind of shallow unitary, what I get is a cluster state. And actually, such kind of picture where a sequential circuit that generate a Kramer-Wanier type duality or Fredkin-Shanka type of duality, if I make a space-time rotation, that indeed becomes some type of symmetry gauges. So my original circuit have a Kramer-Wanier duality that change X to ZZ and also ZZ to X. And in the dual circuit, both of them becomes output bit that live on different sublattice. I can always treat the sublattice on outside the qubit as some type of Z2 gauge potential. And for the even side, I can treat that qubit as some type of Ising matter field. And this type of ZXZ stabilizer actually describe a 1D Ising matter field that minimal couple with the gauge potential. So for the sequential circuit perspective, if you make a space-time rotation, I'm doing something like a symmetry gauging, where I minimal couple with the Ising matter field live on one of the sublattice with the gauge potential that live on the link or live on the other type of sublattice. And finally, if I make a measurement on one of the sublattice, which can be treated as a gauge potential, then such kind of measurement in the X direction is something like Higgsing. I fix the gauge potential and finally I Higgs the gauge potential and end up with a symmetry breaking field, which is a GHZ state. So in this picture, it turns out that through a space-time duality, a sequential circuit that implement any type of Kramer-Wanier duality under space-time rotation can be treated as a symmetry gauge. And if I make a measurement on one of the odd sublattice, I'm fixing the gauge potential and hence end up with a symmetry breaking state. And the reason that I can always have a measurement feedback protocol is that such kind of cluster state literally describe Ising matter field minimal couple with the gauge potential. So it has a gauge symmetries. And hence, if I want to do some change on the gauge potential, that is equivalent as doing some type of symmetry transformation on the matter field. So if I make a measurement without post selections and end up with some type of minus X state that I don't want, all I can do is I can just put a string of X operator that make a symmetry transformation on all of the matter field to correct the result and finally end up with the GHZ state I want. Okay, so in this picture, it turns out that there is a pretty simple way to relate sequential circuit with the measurement feedback circuit through a space-time duality. The sequential circuit is a highly non-local unitary gate, but in each steps, we only entangled 2 qubits. For 1D sequential circuit and for higher dimensional sequential circuit, we only entangled the first row with the nth row. And hence, after we implement a space-time rotation, that can always be visualized as a shallow non-unitary circuit where I just apply finite depths of gate together with a measurement that match the qubit on one of the sublattice to be the same as the qubit for my input sequential circuit. And in this picture, the Kramer-Wanier duality, which is implemented by the sequential circuit under space-time rotation, becomes symmetry gauging, and such kind of measurement becomes something like I fix the gauge potential and hence doing something like Higgsing, and that is why I eventually end up with a symmetry breaking ground state. And in this duality, it turns out that the unitary time evolution of the first qubit eventually becomes my input bit that are entangled EPR pair between even and odd side. And the initial qubit for all of the other side turn out to be one of the part of the output bit that live on one of the sublattice. And that is why eventually I have to do a measurement of them in one of the bases to make sure that the resulting post-measurement wave functions exactly match the output bit of the sequential circuit. So this is the general picture of that. And based on that, concurrent question one may ask is, whenever we say or mention something about the duality, usually it's a two-way connections. A can be due to B and B should be able to do back to A. And for a sequential circuit, if I just make a space-time rotation, literally becomes a shallow non-unitary circuit. But can this duality be due back? And this would be a bit tricky because for a unitary gate after space-time rotation, it's always a non-unitary gate. But if I pick up a non-unitary gate and do a space-time rotation, there's no guarantee that you will end up with unitary operators. So obviously, not all of the measurement feedback circuit can be due back to the sequential circuit. And the question is, what type of measurement feedback circuit can be due back to that? And this goes back to Rubin's questions. So there's a certain type of MPS tensors that can be prepared by a unitary gate. So think about a two-body unitary gate. I have an input state and an output state for the first bit. And for the second bit, I have some type of random input state, and then I have the output state. Now I make a space-time rotation such that the input state and output state of the first bit becomes a MPS tensor, and they become the virtual qubit that live on the left and the right leg of an MPS tensor. And the output bit from the second becomes the physical leg of an MPS tensor. So if an MPS tensor can be prepared by such kind of unitary, then depending on which community you are coming from, sometimes we call them something that is preparable by a unitary circuit. This was actually initially explored by Rubin and a bunch of other people almost concurrently about measurement feedback circuit. So knowing that if I have an MPS tensor that can be due to such kind of sequential gate, then for the MPS tensor, what we need is I have a bunch of tensor, and then I just contract their tensor legs and finally get a higher dimensional wave function. This is in the x direction. If I rotate this x to the t direction, the tensor contraction just becomes unitary time evolution. I have the first bit as the input and output state. And then if I contract them in the time direction, this is something like an identity time evolution. And in the second steps of the sequential, this is my input state, and this is my output state. And if I repeat this process, a sequential gate, the first bit encounter with an unitary time evolution between different steps. And if I just do a 90-degree rotations and rotate this vertical red line, which is the trajectory of the first bit into the spatial directions, then that just becomes the tensor contractions. I contract the tensor and let them be the same and eventually get a higher dimensional wave function where the information are coming from the physical bit. So in this dual picture, it turned out that the time evolution of the sequential circuit of the first bit just becomes connecting the MPS tensor where I contract the left leg and the right leg from adjacent MPS tensors. And in the sequential circuit, the second and third and so forth, their output qubit just becomes the physical leg of an MPS tensor after you contract them together along the x direction. So in this picture, it turns out that for the 1D, especially 1D sequential circuit, this is nothing but the MPS representation. And this also tells us that why sequential circuit cannot, in 1D cannot generate any critical state. From the gate perspective, I only cut finite number of gates, so you should only have short range entanglement. And from the MPS language for finite dimensional MPS, you will never get a critical state, at least in 1D. Okay. So previous slide, we showed that the sequential circuit can be viewed, if I make a space-time rotation, can be viewed as contracting an MPS tensor and get a higher dimensional wave functions. And in the meantime, such kind of contractions of the MPS tensor also have quite a lot to do with the measurement feedback circuit, which was actually explored by 4 groups almost concurrently last years. So for MPS tensor, for each tensor, we have a virtual leg, and we have 2 virtual legs and 1 physical leg. And I can also visualize it as 3 qubit clusters that are somewhat locally entangled. And I first prepare a bunch of locally entangled clusters, and to connect them, into an MPS wave function, or in the space-time duality picture, doing a sequential unitary. This is equivalent as for the two virtual cubes from adjacent tensors, I do an EPR measurement. And if it's a symmetric EPR pair, this is nothing but a contraction of the tensor. And if it's other type of EPR result, depending on the MPS symmetries, we can always do a measurement feedback protocol by doing some type of operator that live only on the virtual, on the physical leg, or push all of the operators on the very left or very right boundaries. So this is the measurement feedback circuit under such kind of MPS picture. And such kind of duality actually tell us that the disorder operators in measurement feedback circuit is related with the auto-correlators in the sequential circuit. So when we think about quantum phases, especially symmetry breaking phase, the two useful characters is either we can measure the correlation functions or we can measure the disorder operators. And in general, these two disorder operator versus correlation functions are due to each other and behave in totally different way in the same phase. For example, if I'm thinking about 1D Ising symmetry breaking, I can define a disorder operator, which is an open string of X operators. And in the symmetry breaking phase in 1D, it decays exponentially with the length of the disorder operators, while in the disorder phase, the charge can be localized, so it turned out to be constant. And if we implement Kramer linear duality, this disorder operator just becomes the 2-point correlation functions of the charge operators. And in the measurement feedback protocol, which can always be characterized by such kind of MPS tensors, a disorder operator is something like I apply a bunch of X operators on the physical leg. And because of the MPS symmetries, a string of X operator or string of charge operators can always be decomposed as an X operator, which live on the very left of the virtual leg and the very right of the virtual leg, which is more like the twisted boundary conditions. And if we do the space-time rotation, previously this red lines going in the horizontal direction goes as X. If I do a space-time rotation, this goes as T, and this red line becomes the time evolution of the first bit. And measuring an operator, putting an operator on the left and the right bound becomes putting in operators from time t equals 0 and putting another operators at time t equal t for the first bit. And then the disorder operators, where we check how it scales with the size of the open string, becomes the auto-correlators, where I measure the correlation function in the temporal direction of the first bit that are separate by t times of interval, where t is at the scale of L here. So that indicates that in such kind of duality picture, the disorder operator and scaling with the X eventually becomes the autocorrelator of the sequential circuit, which measures the X charge on the first bit from time to time. And it is understandable that if I have a sequential circuit that would eventually generate a symmetry breaking wave function like a GHZ state, the sequential unitary want to delocalize the charge in order to get a GHZ state. And hence, if I have a charge, initially have a charge here, the unitary gate want to spread the charge and make it delocalized. And that is why it have to exponentially decay with the time along the sequential time direction. And in this order phase, the unitary gate want to localize the charge. So eventually, at this time and later time, we have a large probability to figure out there is a charge operator still localized at the same direction. So here, to summarize, it turns out that some part of the measurement feedback circuit that can be due into a matrix product state can all preparable by sequential circuit can also be due back to the sequential circuit. And in this picture, when we think about measurement feedback protocols, we're actually thinking about MPS state, where we bring about a bunch of locally entangled clusters and connect their virtual legs in terms of EPR projections. And if I take this virtual leg contraction process as a time direction, that just becomes identity evolution of the first bit between two sequential gates. And in this picture, it turns out in the sequential circuit, the autocorrelator of the same qubit live on the first side in time can be due to the disorder operator of the measurement of the state prepared by the measurement feedback circuit and show how do they localize or delocalize in the spatial direction. Okay, so finally, let me just comment a bit about the outlook of such kind of duality. So today I just tell a very simple story. It turns out that the sequential circuit, that is a linear depth unitary gate versus measurement feedback circuit, that is a shallow non-unitary gate, are just simply connected in terms of the space-time duality. So both of which are pretty well-known stories. In sequential circuit, we know that they cannot generate anything beyond the area law, so definitely not anything like a 1D critical state or 2D Fermi surface, but it can still engender quite a lot of interesting state, like some general string net state or the, say, the chiral, the quantum Hall wave functions. In the meantime, for the measurement feedback circuit, you know that if you want the feedback protocol, there are a bunch of non-abelian state like the Fibonacci anion that you cannot do, but still can engender a lot of interesting non-abelian states like the D3 non-abelian state. So what does this space-time duality tell us, other than just showing that there is some internal relation between sequential versus measurement feedback in terms of the space-time rotation picture? So the first thing I would like to comment about is the error in both circuits. So when we think about measurement feedback circuit, what we do is first we have a shallow unitary, usually some type of CZ gate, to locally entangle different qubits. And then for partial degree of freedom, we make a measurement with feedback. And after measurement, the output state are long-range entangled. And there could be a bunch of errors appear during this process. For example, first, the CZ gate can be slightly perturbed to other type of unitary gate that at the time is not just a power 4 and doesn't need to be a Clifford gate. And also in the measurement process, and think about that we are not measure them that are perfectly aligned in X direction. We can just measure them in some tilted direction and see what is going on. And actually, a few years ago, both Matthew Fisher and also Guoye and Ruben figure out that a different type of error can engender a phase transition in such kind of circuit. For example, if I only have error in the measurement direction, I don't measure them in X direction, but I slightly rotate the angle I measure. Indeed, the wave functions, at least in 2D and higher, can engender a critical wave function that is reminiscent of the random bound Ising model along the Nishimori lines. And by continuously rotating this measurement angle, one can drive a phase transition between the ferromagnetic phase to paramagnetic phase. And from this space-time duality picture, it turns out that the even and odd sublattice and different degree of freedom, they correspond to the input and output state of sequential circuit. So if I'm doing some type of rotation of the final measurement, this is something like I slightly perturb my input state that are not perfectly aligned in the plus X direction, just to rotate them into some random angle. And again, apply the same sequential circuit. And by continuously vary this angle, the question we want to answer is whether such kind of sequential circuit can also drive a phase transition from a ferromagnetic phase to paramagnetic phase, barely changing the input state, because the input state are nothing but the output state of the measurement feedback circuit. And the other outlook I want to talk about is the steady state in open quantum system that is related with sequential circuit. So if I have many-body wave functions and I put it in the fridge and let it interact with the environment degree of freedom, it would inevitably entangled with the rest degree of freedom coming from the environment, and in general becomes a mixed state. Such kind of process is known as decoherence, which can be either characterized by a quantum channels or finite or infinite time being Bladian evolutions. And there are several scenarios we are interested about it. First, if I just have finite depth quantum channel or just a finite time being Bladian evolutions, what does the mixed state look like, and whether I still have all of the information I have in my previous pure wave function. And the other is if I let this time to evolve for long enough, what is the steady state of a long-time Lagrangian evolution in open quantum systems? Or what is a steady state if I apply a quantum channel repeatedly for an infinite number of times? So what is a quantum channel? Because these two are indeed the same. A quantum channel is something like I have a huge blue dot. This is my system of interest. It can be one qubit if you are dealing with single body physics, or a row of qubits, or a layer of qubit, whatever. And if I apply a unitary gate to entangle it with the ancillary degree of freedom, which are some locally entangled qubit that coming from the environment after one step, and I assume that the ancillary degree of freedom from the environment, which is this hollow red dot, is not accessible. I have no information about that. Then what I can do is trace it out, and eventually my input state after this quantum channel just becomes a mixed state. And this process can be repeated many number of times. And after that, I get a mixed state undergoes infinite depths of quantum channel. And this is known as the steady state of a quantum channel. And if I do a space-time rotation of this picture, then that indeed becomes sequential circuit. So for each quantum channel, I entangle the first bit with the second bit, and then I trace out the second bit, their output state, and get a reduced density matrix of that. If I make a space-time rotation, if I treat the first bit as the system of interest, and the second bit, any other qubits, as the environment degree of freedom, in the first step of the sequential circuit, I entangle the first and second, and then trace out the second. This is one depth of sequential circuit. And I can repeat this many number of times. In each depth, my first bit is always the system of interest. And the nth bit is actually some ancillary from the environment degree of freedom that is coming from, that serve as a quantum channel that feed the first bit with some type of quantum channel and get another mixed state. If I repeat this process a number of times, then I'm getting a sequential circuit. If I do not trace out all of these bits, this is nothing but a sequential circuit in higher dimensions, where the first row of qubits is the system of interest, and everything else is actually the answer. And if I trace out all of the bits in once, then I'm getting a reduced density matrix of a higher dimensional wave function that is sequentially generated. So in this picture, it turns out that a steady state of an infinite depth quantum channel is equivalent to the reduced density matrix of a higher dimensional wave function that can be sequentially generated. And studying the steady state of a quantum channel or Lagrangian evolution is equivalent as studying the reduced density matrix of a higher dimensional wave function that can be sequentially generated. And in the meantime, because for such kind of sequential circuit, if I do a space-time rotation, this is indeed similar as the MPS picture, where the time evolutions between different depths becomes tensor contractions of an MPS tensor, and all of the output state of the second bit and beyond becomes the physical length of the MPS wave functions. Then the steady state of a sequential circuit indeed becomes the MPS or transfer matrix spectrum of such kind of MPS wave functions. And if we want to figure out that there are any interesting steady states such that your Lagrangian evolution, their real spectrum have some type of degeneracy or symmetry breaking, this is equivalent as looking into the transfer matrix of such kind of MPS tensor and figure out whether there are any spectrum, whether there are any type of degeneracy in their entanglement spectrum. And the third outlook is about how can we measure some type of nonlinear quantities by combining both sequential and measurement feedback circuit. So when we measure a quantity in a pure wave function, the typical thing we can do is for symmetry breaking phase, we can either measure the 2-point or finite point correlation functions or measure the disorder operators. However, if we get a symmetry protected topological phase, what we usually need to measure is some type of strange correlator, where I have an SPT wave function. I measure the usual correlation function, so I have a correlation function acting on the SPT wave function. And then I want to interproduct with a trivial state, which is just an on-site tensor product state, normalized with their overlap. This is known as the strange correlator. And turns out that for SPT wave function, such kind of the usual correlator is always short-ranged, but the strange correlator can either exhibit long-range or at least a quasi-long-range order. However, thing we have in mind is how do we measure such kind of strange correlator in reality, because that would always involve, you want to check the inner product between a wave function, which is already prepared, and a trivial wave function that is usually a tensor product of on-site state. So first, for many SPT wave functions, they can always be generated via sequential circuit. For example, if I have a 1D, say, AKLT chain of P-wave superconductors, I can begin with a trivial state where two Majorana fermions on the same side are just locally hybridized. And if I want to apply sequential circuit to get a P-wave superconductor, all I need is a swap gate, which exchange the right Majorana with the other right Majorana on nearest neighbor site. And this would transform the intra-unit cell entangled Majораnas into inter-unit cell entangled Majораnas. And if I repeat this process, I eventually get a P-wave superconductors, and these two Majorana fermion hybridization can be treated as the other boundary. And finally, we have a fixed boundary conditions. So if I have a sequential circuit and prepare such kind of P-wave superconductor or SPT phase, and I want to measure the strange correlator, the thing we can do is, because we only need their overlap between an SPT state and trivial state, and the trivial state can just be some type of on-site tensor product state. So I can measure all of the bit on some specific basis and get the outcome. And after each measurement, the outcome is usually random. I would not always get zero state. And the question is, if I get other type of state, which correspond to another type of trivial state, how can I correct them without post-selections? And the trick here is, in principle, SPT wave function that can be generated by sequential circuit can be combined with the measurement feedback protocols. So what I'm doing is I'm not generating the wave function in terms of sequential circuit in one step and measure them. Instead, the first step is I use a partial swap gate to locally entangle the first and second bit, and then measure the second bit, say in the parity basis or in some basis. And if this is not a result I want, then that should be correspond to, I have to apply some unitary gate here acting on the zero state. And such kind of unitary gate can always be feedback or feed forward to a unitary gate on the first bit before I apply the second swap gate. And then I apply the second swap gate and again measure the third bit. Depending on its outcome, I can decide which type of correction operators I should feed forward on the first bit before I apply to the next step of the sequential circuit. By implement such kind of measurement and feed forward and incorporate them in a sequential circuit, this is exactly the same as I'm doing some type of projective measurement to force them to be a specific patterns. And this indeed figuring out how to calculate the inner product between an SPT wave functions and the trivial wave functions. So another coloring we can figure out is that by combining sequential circuit and a measurement feed forward circuit, principle one can measure a zoology of nonlinear operators, like checking the overlap between an SPT state and an on-site trivial state. So I think I'm running out of time, and let me just end here and let me acknowledge my collaborator again and take questions.
Thanks for the very nice talk. So, questions?
Hi, thank you so much for your talk. I was just wondering, would you mind elaborating the one part where you were talking about how the virtual connecting corresponds to EPR pair projections? I think it was the one slide you were talking about qubits of SC.
Yeah. So
Yeah.
I think this was Ruben's protocol about what type of wave function can be used by measurement feedback, and turns out that it may need to be NPS type and you need to have NPS symmetries. So when I contract these two tensors, this is something like enforce this leg and this leg to be the same. And if I project it, let's forget about feedback, just project it to the symmetric EPR pair. This is something like once the left is in the I state, the right is also in the I state.
Oh, okay. So is it like on, I guess, the left diagram, are there also technically like measurements between the virtual bonds, or is that?
Yes,
like,
it's always measurement between two adjacent virtual bonds. The right leg here and the left here
Oh,
between
okay.
two adjacent clusters, and each cluster is something like an MPS tensor.
I see,
And
so
once you
that's,
connect them, once you connect these legs or doing measurement, then you can generate long-range correlation between the physical legs you want.
I see, then what are the, would you mind reminding the green lines on the left diagram?
Yeah, so the green lines here is, the green line, this is my input state.
Oh,
And
okay.
this is my output state, and the output state
gotcha.
of the ice qubit literally becomes the physical leg of the MPS tensor from the nth cluster.
Okay. Thank you.
Michael?
I'm just wondering, you mostly focused on 1D systems here,
Mhm.
so to what extent do some of these ideas generalize to, say, two-dimensional systems?
So for 2 dimension, it's something like either we have to entangle it row by row, like if I want to generate something like a toric code, what I have is in the sequential circuit, it's something like I apply a row of unitary gate on the first row of plaquet, which can be implemented simultaneously to entangle the first and second, and then do it repeatedly. And the only difference is something like the dot, which I plot previously. It's not just in the very beginning. It's not just a one qubit. It actually corresponds to a row of qubits. Or in some cases, like if you want to get a 2D GHZ state, the protocol is first we have to highly entangle the first row and make them a GHZ state, and then apply the something like the CZ gate on all of the X bar from the second to the third and do it. And what I do is actually first I make a space-time rotations for the first row of qubit and get a highly entangled state and treat this as my initial input state to entangle the rest. However, the issue is such type of protocol, if generalized to higher dimension, usually work pretty well for such type of CSS code. But if you want something like a quantum double model, which can be implemented in terms of sequential circuit or other type of string net model, which can always be implemented in terms of sequential circuit, I'm not sure whether there is a simple way to do it into the measurement feedback circuit, because for the stabilizer code, usually the unitary gate can be tuned to be a control gate together with a swap gate. And after space-time duality, Q is still also a unitary. If it's a general unitary gate, then this Q might be non-unitary. And a non-unitary gate can always be decomposed into a unitary gate together with some type of projection or partial projection. And the issue is, if we want to implement a circuit, a projection is usually a projection is more like a measurement with post-selections. And to avoid post-selections, then usually we need some type of measurement feedback protocols. But for a general Q gate, there is no guarantee that you can always find measurement feedback protocol. So in higher dimension, it's pretty limited unless you are thinking about any wave function that is just a ground state of some cluster state or CSS code.
Any further questions? No other questions? Let's thank the speaker again.